thank you for joining us. Today we are going to be looking at modern water purification using osmosis, nanomaterials, and filtration techniques. Imagine waking up one morning and turning on your tap only to find water cloudy, tasting strange, or even unsafe to drink. This is a reality for millions of people around the world who struggle with polluted water sources. Clean water is vital not just for drinking, but for cooking, cleaning, and even industrial laboratory use. Over time, scientists and engineers have worked hard to develop better ways to purify water, removing harmful substances like salts, germs, chemicals, and heavy metals to make water safe and healthy. It's reverse osmosis, a process where water is forced through a special filter that acts like a gatekeeper, allowing only pure water molecules to pass while blocking nearly all impurities. But what if we could make this process even better? That's where nanomaterials come in. These tiny, powerful materials like nanofibers and nanoporous polymers have super small pores and huge surface areas, enabling them to catch even the smallest contaminants that regular filters might miss. This also helps filter last longer and work more efficiently. In this presentation, we explore how combining reverse osmosis with nanomaterials-based filtration can create a powerful water purification system. By testing how well these methods remove different contaminants, we aim to find the best way to deliver clean, safe water to homes, factories, and labs so everyone can turn their taps with confidence.
Nanoporous polymer are advanced material characterized by their network of nanometers scale pores, which provide a high surface area and a tunable porosity. This feature has made them particularly effective for water filtration application. In water treatment, nanoporous polymer membrane function by selective allowing water molecules to pass through while blocking contaminants such as salt, heavy metal, organic compound, and microorganism. This selective is achieved through mechanism like size exclusion, where the pore size is designed to be the smaller than the unwanted material, and through chemical interaction that repels specific contamination. The facility in designing this membrane enable them to target a wide range of pollutant, making them suitable for application range from desalination to water waste treatment. Moreover, this structural stability and potential for functionalization analyze their performance and durable in various filtration systems.
Nanofibers are ultra-thin fibers with diameters in the nanometer range. When applied in water filtration, nanofibers offer several benefits. The advantages of nanofibers in water filtration are high surface area, small pore size, flexibility, and versatility. Applications of nanofibers in water filtration include microfiltration and ultrafiltration, removal of heavy metals and pollutants, drinking water treatment, and wastewater treatment. The types of nanofibers used in water filtration include polymeric nanofibers and composite nanofibers. The challenges and future direction in nanofibers: scalability and cost effectiveness, fouling and durability, research and development. Nanofibers offer promising solutions for water filtration, and continued advancements in this field are expected to improve their performance and applicability.
During a school field trip to a local water treatment plant, the guide stops at the large tank filled with Mercury River water. A group of students gathers around as the guide begins to explain. The guide says, "This is where coagulation happens. We add a coagulant, usually alum, which helps tiny particles in water to stick together. These particles are too small to settle or filter out on their own, but when we add alum, it neutralizes the charge. That makes them clump together into bigger, heavier particles called flux." He then points to the water now forming visible clouds. These flux can now settle out in the next stage, sedimentation, where gravity pulls them together. After that, we filter and disinfect the water.
Imagine pouring muddy water into a glass and letting it sit for a while. Over time, the dirt settles at the bottom, leaving clearer water on top. This natural process is called sedimentation, and it's used in water treatment to remove unwanted particles before filtration. One would ask oneself, Why is sedimentation important? Sedimentation is important because it helps remove things like sand, soil, and other heavy particles from water by allowing them to settle in special tanks. That's where we make the water cleaner and easier to filter. How does sedimentation work? Well, the first step is that water enters a tank where it is kept still. Then the heavy particles start sinking to the bottom because of gravity. Then clear water remains on top, ready for the next stage of purification. The limitations of sedimentation are that it only removes larger impurities. It cannot remove very tiny particles, bacteria, or dissolved chemicals. That's why it is followed by filtration and disinfection to make water safe for drinking. Sedimentation is like the first step in cleaning water. It removes big particles, making the next stages easier and more effective. Without it, filtration would be much harder and less efficient. So the next time you drink a clean glass of water, remember that sedimentation helped make it possible.
Hi, I'm Rile, the voice behind the character you're seeing on the screen right now. Please note that you will only be able to see my face at the end of this video. Today, I'm going to take you on a journey inside a water molecule to discover how reverse osmosis purifies water and why it is one of the most effective filtration methods in the world. So sit tight and relax as we embark on this journey together. One of the most asked questions is what exactly is the role of reverse osmosis in the purification of water? And before I can actually answer that question, let's first look at what I mean by reverse osmosis as well as its principle. When you think about reverse osmosis, just know that it is the opposite of osmosis, because in normal osmosis, the water that is highly concentrated with things like salts, heavy metals, bacteria, and viruses diffuse from a low concentrated area to a highly concentrated area. However, in reverse osmosis, pressure is applied to water that is highly concentrated with things like heavy metals, salts, bacteria, and viruses in order to move it backwards through the membrane from a highly concentrated area to a low concentrated area, in doing so, trapping all the contaminants in the semi-permeable. Displayed on the screen right now is a full detailed diagram of reverse osmosis. I'm kidding. I'll be using a much more detailed diagram in my next slide to explain to you guys the whole process for reverse osmosis.
As promised, here is a detailed diagram that explains the whole process of reverse osmosis. First, we have the raw water tank. This tank is responsible for storing the untreated water from our source and acts as a buffer that ensures that there is a constant supply of water throughout the system. We then have the raw water pump that is responsible for pumping water from the raw water tank into the pre-treatment stages by providing the initial pressure that is needed to move our water through the sand, carbon, and other filters before entering the reverse osmosis membrane. The sand filter is then used to remove large particles such as sand, slate, and rust in order to protect the downstream filters and prevent the membrane from clogging. We then have our activated carbon filter, which is used to absorb chlorine, organic compounds, and other unusual odors of water. This is done to improve the taste and the odor of our water. The water softener tank is responsible for removing ions like calcium and magnesium, which can result in the hardness of water. This tank is really important because it prevents the damage of our membrane by hard minerals. We then have our precision filter that captures the fine particles that have managed to bypass the earlier filters, acting as the final pre-filter treatment of our water.
Down over here, we have a high pressure pump. Why another pump, do you ask? Well, this pump is used to increase the pressure of water to a level that is needed for reverse osmosis to take place in the semi-permeable membrane. Now, when we increase the pressure of our water, we are able to overcome the natural osmotic pressure. As you can see, our reverse osmosis membrane is not really clear in this diagram. However, don't worry, I will be covering a much more detailed version of it in the next slide. Lastly, we have our pure water tank. As the water leaves the reverse osmosis membrane, it enters the pure tank where it will be stored and used for supplying our communities, or it can be used for further sterilizing using UV light. Osmotic pressure is overcome, resulting in water moving backwards through the semi-permeable membrane. Now, here in the semi-permeable membrane, the dissolved salts, heavy metals, bacteria, and viruses are blocked. This right here is known to be the core purification step in the whole process, where only clean water molecules are allowed to pass through, leaving all the contaminants trapped behind.
Let's talk about the advantages of using a reverse osmosis. It's a powerful and efficient method of water purification. It effectively removes a wide range of contaminants, removing chemical impurities, harmful germs, dangerous viruses, and even toxic heavy metals like lead and mercury. But that's not all. Reverse osmosis also tackles unpleasant tastes and odors, often caused by chlorine, organic compound, and other contaminants, leaving your water clean, crispy, and refreshing. Maintenance. It's minimum. Reverse osmosis systems are designed to be low maintenance, making them convenient choice for household and business alike. It's also energy efficient, unlike thermal distillation, which consumes significant energy for heating. Reverse osmosis rely on advanced membrane technology, saving both energy and cost. Experience the purity of reverse osmosis, clean, safety, refreshing water with every drop. Let's talk about the advantages of using a reverse osmosis. It's a powerful and efficient method of water purification. It effectively removes a wide range of contaminants, removing chemical impurities, harmful germs, dangerous viruses, and even toxic heavy metals like lead and mercury. But that's not all. Reverse osmosis also tackles unpleasant tastes and odors. The limitation of using reverse osmosis in water purification. Depending on the system, reverse osmosis may waste 3 to 4 liters of water for every liter of filtered water generated. Despite being more effective than thermal technique, reverse osmosis still uses energy for high pressure pumps, particularly in systems that are huge in size. Reverse osmosis removes not only harmful contaminants but also essential minerals like calcium. The reverse osmosis membrane can be easily damaged by chlorine, sediment from biological growth requiring pre-treatment or regular maintenance. Reverse osmosis filtration can be slowly, especially in household units, due to the need for water to pass through the membrane under pressure. The limitation of using reverse osmosis in water purification. Depending on the system, reverse osmosis may waste 3 to 4 liters of water for every liter of filtered water generated. Despite being more effective than thermal technique, reverse osmosis still uses energy for high pressure pumps, particularly in systems that are huge in size. Reverse osmosis removes not only harmful contaminants but also essential minerals like calcium. The reverse osmosis membrane can be easily damaged by chlorine, sediment from biological growth requiring pre-treatment or regular maintenance. Reverse osmosis filtration can be slowly, especially in household units, due to the need for water to pass through the membrane under pressure. The limitation of using reverse osmosis in water purification. Depending on the system,
Technologies such as reverse osmosis, nanomaterials, and advanced filtration techniques offer effective solutions to address the growing concerns of water pollution and scarcity. These technologies have shown promising results in removing emerging contaminants, pathogens, and heavy metals from water, thereby improving water quality and public health. As the global demand for clean and safe drinking water continues to rise, the adoption and implementation of these modern technologies will play a crucial role in ensuring sustainable water management and community resilience. Further research and investment in these technologies will be essential to address the evolving challenges of water purification and providing clean water for future generations. Thank you.